January 5, 1943, between 0 and 18 hours. USS Helena, Guadalcanal. Lieutenant Russell Cochrane stood at Mount 52's firing controls, tracking a Japanese Val-dive bomber slicing through moonlit clouds toward the American cruiser formation. His finger tightened on the trigger as the plane approached within 28 yards. Unaware of the advanced technology his shells contained, details he himself hadn't been fully briefed on, he received the order to commence firing over his headphones. The 5-inch gun unleashed a deafening roar, sending its projectile skyward at an incredible speed of 26 feet per second. Within the shell was a compact radar unit no bigger than a light bulb, emitting radio waves and listening for their reflection. When the return signal indicated that the aircraft was within 70 feet, the fuse detonated automatically. The bomber disintegrated at a distance of 21 yards from Helena, shattered by an explosion that never made contact with the plane itself. Lieutenant Cochrane had just achieved the first verified combat kill using proximity fuse technology, though this accomplishment would remain classified for another 2 years. The innovation within that shell, officially designated VT for variable time to conceal its true purpose, revolutionized naval warfare in ways neither Cochrane nor the Japanese pilot could have foreseen. By war's end, this fusion of radar and explosives had destroyed thousands of kamikaze aircraft, rendering Japan's desperate weapon ineffective. The calculus of survival was being written in vacuum tubes and radio waves. In just 2 years, proximity fuses achieved what bravery and conventional weapons alone could not: the systematic defeat of pilots willing to sacrifice their lives. The kamikaze threat emerged from strategic mathematics that offered Japan no viable solutions. By October 1944, following the devastating losses at the Philippine Sea Battle, where American forces obliterated 645 Japanese aircraft while losing only 123, conventional aerial attacks had become futile exercises for Japan. Vice Admiral Takejiro Onishi, in charge of the 1st Air Fleet in the Philippines, faced grim arithmetic: fewer than 100 operational aircraft against an American invasion fleet exceeding 700 ships. On October 19, 1944, at Mabalacat Airfield, he presented his solution to the staff of the 200th 1st Air Group. Captain Rikihei Inaguchi meticulously documented his precise statements. He believed that only fervent young men prepared to crash their planes into enemy carriers could save our nation. The rationale appeared unassailable. Standard bombing raids yielded hit rates of less than 10% against maneuvering warships, whereas a pilot-controlled aircraft aimed for impact might theoretically achieve success rates of up to 50%. In Japan's dire calculations, this strategy offered potential salvation. One pilot equated to one aircraft and possibly the sinking of an enemy vessel. The inaugural coordinated kamikaze assault occurred on October 25, 1944, when Lieutenant Yukiyosuke led 50 fighters from the Shimpu Special Attack Unit against American escort carriers in Samar. Each plane was laden with a 250-kilogram bomb, and each pilot carried letters to their loved ones as well as photographs of Emperor Hirohito. They managed what months of conventional attacks had failed to achieve: direct hits on American carriers. USS Santee suffered a kamikaze strike, resulting in the death of 16 sailors. Minutes later, USS Suwannee was also struck. Commander David McCampbell, who held the Navy's record with 34 victories, noted in his action report, "This is an attack method that cannot be entirely prevented." He emphasized that no amount of pilot expertise could ensure interception of every attacker. The enemy had effectively weaponized death itself. Prior to the widespread use of proximity fuses, naval anti-aircraft defense relied on 3 critical systems: each with inherent limitations exploited by kamikaze tactics. 5-inch 38 caliber dual-purpose guns made up the outer defensive layer, effective against targets between 10,000 and 18,000 yards. The shells used were equipped with mechanical time fuses that needed to be manually adjusted before loading. Fire control officers relied on the Mach 37 gun fire control system, an analog computer designed to calculate where an aircraft would be by the time the shell arrived. This system was effective against a steady and predictable bomber flying at 200 miles per hour while maintaining a constant altitude. However, it proved inadequate when facing kamikazes traveling at 400 miles per hour in steep dives, constantly maneuvering to evade targeting solutions. Gunnersmate First Class James Morrison from USS Enterprise described the challenges. "We would calculate our trajectory for about 4.5 seconds, expecting the plane to be at 8,000 feet, but the kamikaze pilot would dive, climb, or make sudden maneuvers to throw off our aim. By the time our shell exploded, it was often hundreds of feet away from its intended target. The geometry involved in hitting such fast and unpredictable targets seemed insurmountable with their arithmetic-based calculations. The 40mm Bofors guns offered a mid-range defense between 4,000 and 6,000 yards. These weapons fired contact-fused shells that required direct hits to be effective. Against a kamikaze, presenting a frontal target of less than 80 square feet, while diving at speeds ranging from 400 to 500 miles per hour. Hitting the aircraft was exceedingly difficult. Statistical analysis revealed that the probability of a single round making contact was under 0.3%. Chief Petty Officer Harold Stassen, who commanded a quad 40mm mount on USS Hornet, testified about their efforts. "We would fire 480 rounds per minute with shells everywhere, yet we watched kamikazes fly right through our defenses. Even when we hit them, unless we disabled the engine or killed the pilot instantly, momentum would carry the plane into the ship." The 20mm Oerlikon cannons served as the last line of defense within a range of 2,000 yards or less. Once kamikazes reached this distance, impact was typically only 5 seconds away. These weapons fired small shells that required multiple hits to cause structural damage. Seaman First Class Robert Baker, an Oerlikon gunner on USS Missouri, recounted his experience. "At 2,000 yards, you had maybe 4 seconds. Your mind went blank. All you could do was hold the trigger and pray. Even if you shredded the wings, the fuselage kept coming." The development of proximity fuses did not initially aim to counter kamikazes, but rather German bombers over London during the 1940 Blitz. Anti-aircraft batteries in Britain required an average of 18,500 shells to bring down a single bomber during that period. The mathematical calculations proved impractical. Shells needed to be set for specific altitudes, while bombers frequently altered their heights. A shell exploding just 100 feet away from a bomber caused no harm, but one detonating within 30 feet was deadly. In September 1940, Sir Henry Tizard traveled to Washington with Britain's most critical military secrets contained in a black metal deed box, which was offered to America without reservation in exchange for production capabilities. Among these secrets was an idea for miniaturized radar that could fit inside artillery shells. This project was assigned to Section T of the National Defense Research Committee, headed by Dr. Merle Tuve at what would become the Johns Hopkins University Applied Physics Laboratory. The challenges appeared insurmountable. They had to create a device smaller than a coffee cup, robust enough to withstand 20,000 times the force of gravity upon firing, sophisticated enough to differentiate between aircraft and ground returns, and inexpensive enough for mass production. The breakthrough came from physicist James Van Allen, who later discovered Earth's radiation belt. He suggested using hearing aid vacuum tubes, the smallest available, which might survive the extreme acceleration caused by gunfire. These tubes, originally designed for deaf patients' earpieces, had to operate after enduring forces that would crush standard electronics. By December 1942, the team had produced a functional prototype. The Mark 32 fuse consisted of 5 vacuum tubes, a battery activated upon firing, an oscillator generating radio waves at 180 megahertz, and a Thurotron switch triggering detonation when a return signal indicated a target within lethal range. The entire device was just 3 inches long and weighed 11 ounces. The first combat test took place on January 5, 1943, with the USS Helena, but widespread Pacific deployment awaited the resolution of security concerns. The Navy worried that if used over land, the technology could be captured and replicated by adversaries. By October 1944, as kamikaze attacks intensified, the United States had manufactured more than 1 million proximity fuses at $18 each, expensive compared to conventional fuses, but invaluable in protecting ships. Factories in Cleveland, Cincinnati, and Bridgeport were producing 40,000 fuses daily, largely through the efforts of female workers who did not know what they were assembling. Crates labeled as "Special Ammunition Handle with Care" arrived at Pacific Fleet bases containing the fuses. Security protocols were stringent, and most gunnery officers only received basic operating instructions without fully grasping the underlying technology. The shells looked nearly identical to standard rounds, except for a small plastic nose cone safeguarding the radio antenna. In November 1944, Captain Willis Lee, who commanded Battleship Division VII, was among the first to receive a significant shipment of proximity-fused 5-inch shells. Commander Edwin Hooper, his gunnery officer, later recounted that they initially thought claims about these shells tripling their effectiveness against aircraft were mere propaganda until they witnessed them in action. The fuses functioned based on sophisticated physics principles. As the shell approached an enemy plane, it emitted radio waves which reflected back with increasing intensity. When the returning signal indicated the target was within lethal range, typically around 70 feet for a 5-inch shell, the fuse would trigger detonation. The resulting explosion created a sphere of steel fragments expanding at supersonic speeds, each capable of penetrating aircraft aluminum up to 200 yards away. What made these fuses truly revolutionary was their discrimination capability. Rain, clouds, and chaff could not generate sufficient radar return to initiate an explosion. Ground-based returns were filtered out using the Doppler effect, the same principle that causes a train's whistle pitch to change as it passes by. Only rapid closure with an aircraft created the precise conditions required for detonation. The invasion of Okinawa, which began on April 1, 1945, provided the ultimate test scenario for proximity fuses against large-scale kamikaze attacks. Over 3 months, the Japanese launched 10 major waves known as Kikyusui operations, consisting of approximately 19 kamikaze sorties. For the first time, most American ships carried proximity-fused ammunition across all calibers from 5-inch down to 40. The initial Kikyusui assault on April 6, 1945 coincided with Operation Tengo, a suicide mission involving the battleship Yamato. Kikyusui I included 355 kamikaze aircraft and 344 conventional fighters. Radar operators aboard USS El Dorado reported seeing what they described as a snowstorm on their screens at 1,500 hours. A dense cloud of individual aircraft returned signals merging into a solid mass. Fire Controlman Second Class Eugene Hardy, serving on the destroyer USS Newcomb, recounted the intense battle. Enemy aircraft arrived in successive waves. Our 5-inch guns began firing at a range of 12,000 yards. We observed black smoke puffs far away and saw planes plummeting to their demise without diving, appearing as if they had been shattered. The proximity fuses were instrumental in turning near misses into direct hits. The USS Laffey's experience on April 16th was particularly harrowing. Positioned at Radar Picket Station Number 1, the destroyer faced an onslaught of 22 Kamikaze aircraft over a period of 80 minutes. Her crew expended 637 rounds of proximity-fused 5-inch ammunition. Despite being hit by 6 kamikazes and 4 bombs, Laffey emerged intact, her guns having destroyed at least 9 attackers. The proximity fuses created what survivors referred to as an impenetrable steel barrier around the ship. Commander Frederick Bechton, Laffey's captain, stated that the proximity fuses were crucial in their survival. He recounted instances where a kamikaze would close in, and upon our guns firing, the plane would vanish, disintegrated rather than shot down. These fuses transformed defensive fire from a matter of chance into an almost guaranteed success. Statistics gathered during the Okinawa campaign highlighted this dramatic shift. Ships equipped with proximity fuses destroyed kamikaze aircraft at rates 7 times higher compared to those using conventional ammunition, directly translating into saved lives and vessels. Japanese pilots soon realized that a significant change had occurred in American anti-aircraft capabilities, although they never fully grasped what it was. Lieutenant Commander Tadashi Minobi, who accompanied kamikaze missions as an escort pilot, testified after the war about this transformation. Starting from late 1944, he noted that American anti-aircraft fire seemed almost supernatural in its effectiveness, with planes exploding even before being hit by direct fire. Our pilots noted the deployment of what appeared to be invisible wires or aerial mines by American forces. Captured Japanese documents revealed increasing confusion among their ranks. A tactical bulletin from the 201st Air Group, dated December 1944, stated, "Enemy anti-aircraft effectiveness has significantly increased. Shells now seem to detonate based on proximity rather than contact. We recommend irregular flight paths and extreme diving angles." The Japanese military entertained various theories about these advancements. Some speculated that magnetic fuses were attracted to engines. Others believed infrared sensors detected heat signatures, and there were even claims of psychics mentally detonating the shells. They attempted numerous countermeasures, such as wrapping engines in protective material, installing degaussing coils, experimenting with wooden aircraft, but none proved effective against radar-based fuses. Ensign Toshio Yashitake, captured after his plane was damaged by proximity fuse fragments, recounted to interrogators that they had been told American gunners were poorly trained and relied on volume of fire. However, their shells seemed to know exactly where the Japanese planes were. They would explode all around them, creating a wall of metal. Flying through American fire became akin to navigating through a storm of steel. The proximity fuse was an impressive feat of miniaturization and mass production. By 1945, each Mark 53 fuse, the most common variant, contained 134 electronic components assembled with microscopic precision. The complete device had to function after experiencing up to 20,000 times the force of gravity during firing, spin at 30,000 RPM in flight, and operate across a temperature range from -40 degrees Fahrenheit to positive 140 degrees Fahrenheit. Manufacturing these fuses required revolutionary techniques. Workers used jeweler's loops to solder connections smaller than rice grains. Quality control involved testing 1 out of every 500 fuses by firing them. Initial rejection rates exceeded 60%, but improved to under 8% by 1945. The battery itself was a breakthrough in engineering, using a glass ampule of electrolyte that shattered upon firing, activating a wet cell providing power for the duration of flight. This design allowed fuses to be stored indefinitely without experiencing battery degradation. Western Electric created unique winding methods for vacuum tubes, incorporating delicate springs that could withstand acceleration without damage. These innovations ensured that hearing aid vacuum tubes could endure forces that would typically destroy standard ones. Proximity fuses were not merely an improvement. They fundamentally transformed naval anti-aircraft strategy. Prior to their deployment, ships relied on barrage fire, launching waves of shells in hopes of intercepting aircraft flying through them. This approach was extremely wasteful and had a low success rate. Commander Joseph Callahan, tactical officer for Task Force 58, stated that with time-fused shells, the goal was to hit a specific point at a precise moment, which was nearly impossible against maneuvering targets. With proximity fuses, however, it became necessary only to get the shell near the target. The fuse would handle detonation from there. New firing patterns were developed specifically for these fuses, allowing ships to engage multiple aircraft simultaneously with smaller salvos rather than concentrated barrages. A destroyer that once required 50 rounds to achieve a reasonable hit probability could now target 3 aircraft using the same amount of ammunition. Proximity fuses also made night defense effective for the first time. Before their introduction, darkness made accurate range estimation nearly impossible for setting time-fused shells. However, proximity fuses solved this issue by ensuring that shells would detonate at the correct distance regardless of visibility conditions. Lieutenant Commander Roger Bond, gunnery officer on USS Enterprise, reported that night kamikaze attacks had been a nightmare due to blind firing and low hit rates. With proximity fuses, their night effectiveness surged from around 10% to over 70%. By mid-1945, the Japanese had largely ceased nighttime attacks. By the war's end, American factories had manufactured approximately 22 million proximity fuses, equivalent to one for every 6 people in Japan. The initiative involved 87 companies running 110 facilities with security measures on par with those of the Manhattan Project. The Crossley Corporation plant in Cincinnati emerged as the biggest producer, churning out 16,500 units per day during peak production. The factory operated under stringent security protocols, requiring workers to pass through guarded entrances and relinquish personal belongings before entering windowless assembly areas where components were identified solely by code numbers. Quality control was exceptionally rigorous, surpassing previous mass production standards. Every 1,000th fuse underwent testing at Aberdeen Proving Ground. If it failed to detonate within the specified range, the entire batch was discarded. This thorough process ensured combat reliability exceeding 95%. The program consumed vast quantities of strategic materials such as silver, gold, and platinum for electrical contacts, with monthly usage surpassing the annual consumption of the pre-war American jewelry industry by 1945. Both sides acknowledged the significance of proximity fuses, leading to fierce intelligence battles. After capturing examples used against Von flying bombs over England, the Germans attempted to develop countermeasures. The Japanese, lacking captured samples, tried piecing together the technology from combat observations and shell fragments. American intelligence agencies implemented stringent protection measures. Proximity fuses could only be deployed over water until late 1944. When USS Drexler sank at Okinawa with magazines full of proximity-fused ammunition, the Navy considered destroying the wreck to prevent recovery. Commander Joseph Rochefort, head of Pacific Fleet Intelligence, orchestrated elaborate deception campaigns. Force intelligence leaks suggested improved effectiveness stemmed from better training and optical sight enhancements. Captured German agents were given misinformation about magnetic anomaly fuses that detected Earth's magnetic field distortions. During the war, Japan never managed to obtain a fully functional proximity fuse. Their primary source of information came from interrogating captured B-29 crew members, whose knowledge was limited at best. As a result, Japanese scientists pursued fruitless endeavors in developing radio-guided shells. Meanwhile, the U.S. Navy's operational research team conducted extensive effectiveness analyses throughout 1945. The findings, which remained classified until 1958, shed light on the true impact of proximity fuses. Prior to the widespread use of these fuses, from October 1944 to January 1945, Kamikaze aircraft achieved hit rates of 28.7%, counting both direct strikes and damaging near misses. Ships averaged firing 312 rounds per downed aircraft. Destroyer picket ships suffered one sinking or severe damage for every 15 kamikaze sorties launched against them. With the deployment of proximity fuses from February to August 1945, however, kamikaze hit rates plummeted below 10%. Ships now required only 89 rounds per aircraft destroyed, marking a remarkable 71% improvement in ammunition efficiency. The loss rate for destroyer picket ships also dropped significantly, with one sinking or severe damage occurring per 47 kamikaze sorties, despite the Japanese adopting more aggressive tactics. Detailed analysis uncovered strategic advantages of proximity fuses. These weapons proved especially effective against high-angle diving attacks, a favored tactic by kamikazes, achieving success rates exceeding 85% when engaging aircraft approaching at angles steeper than 45 degrees. While effectiveness decreased for low-level approaches, it still surpassed that of conventional ammunition. Captain Willis Lee's action report from April 1945 provided concrete examples of these advantages. On April 16, his force engaged 43 attacking aircraft. Proximity-fused 5-inch ammunition accounted for 31 confirmed kills at ranges between 4,000 and 9,000 yards. In contrast, conventional ammunition fired in parallel achieved only 3 kills despite consuming 40% more shells. Not all ships immediately excelled in employing proximity fuses. The technology necessitated new training, tactics, and maintenance procedures for optimal use. The USS Newcomb's experience highlighted the learning curve during World War II. Initially, the destroyer's crew aimed their radar-controlled guns to fire continuously at maximum speed, which led to electromagnetic interference among multiple proximity fuses and decreased overall effectiveness. On April 6, 1945, 5 kamikaze planes managed to breach their defenses, resulting in significant damage. Lieutenant Commander Irving McPherson, the ship's gunnery officer, reported that firing too many proximity fuses at once caused mutual interference due to radio waves creating false targets. They later adjusted their tactics by coordinating controlled bursts rather than continuous streams of fire. The Navy swiftly adapted and established new doctrines to address these challenges. Ships were instructed to assign specific mounts for the use of proximity fuses, while others continued using conventional ammunition. Fire control teams devised pulse patterns, or rhythmic firing sequences, which minimized interference and maximized coverage. Maintaining these sensitive electronic systems was also crucial. The delicate electronics required protection from environmental factors like humidity, salt spray, and extreme temperatures. Crews discovered that storing fuses in uncooled magazines often led to failures in tropical waters. Solutions included installing dehumidifiers and temperature controls within ammunition storage areas. The proximity fuse program's scale was immense, with production output reaching 22,073,481 fuses from January 1943 to August 1945. This massive undertaking involved 110 production facilities spread across 26 states, achieving a peak daily production rate of 75,000 fuses in total and 40,000 anti-aircraft fuses specifically. The financial cost amounted to $1.2 billion in 1940s dollars, while material consumption included 12 tons of silver per month and 800 pounds of gold monthly. Additionally, the program consumed approximately 15,000 miles of wire daily, and utilized a total of 140 million vacuum tubes. Quality control measures were also stringent to ensure reliability in such high-volume production environments. Combat reliability stands at 95.3%, with a premature detonation rate of 0.3% and a 4.4% malfunction rate, or DUDE rate. Storage stability after 1 year is reported at 99.7%. Japanese records captured post-surrender detail the psychological toll that proximity fuses inflicted on kamikaze units. War diaries from Kanya Air Base belonging to the 721st Naval Air Group reveal increasingly desperate entries throughout 1945. In January of 1945, enemy anti-aircraft fire showed significant advancements. Shells now detonate due to proximity rather than timing devices. Recommendations were made for pilots to maintain a higher altitude until reaching their final approach stage. By March 1945, losses prior to reaching the attack position had risen above 60%. Enemy artillery created an impenetrable barrier around high-value targets, causing morale to deteriorate as pilots recognized that death could occur without achieving impact. In May of 1945, pilots reported encountering solid walls of steel during their missions. Traditional evasion tactics proved ineffective. Requests were made for permission to conduct night attacks exclusively. By July 1945, the daily ration of sake had been increased. Despite this, many volunteers expressed a preference for conventional missions, acknowledging that they offered lower honor but potentially higher chances of survival. The enemy's gunfire seemed to be directed by supernatural forces. Lieutenant Kiyoshi Agawa, one of the rare kamikaze pilots who survived multiple missions due to mechanical issues, testified after the war. "We were prepared to die honorably for the Emperor, but instead we witnessed our comrades' futile sacrifices as they exploded far from their intended targets. Our experience was more like an execution than a battle." The Mark 53 proximity fuse, which became standard by 1945, showcased remarkable engineering prowess. It measured 3.2 inches in length and had a diameter of 2.1 inches, weighing 11.3 ounces. The device consisted of 134 individual components, including advanced electronic systems, with an oscillator frequency ranging from 180 to 220 megahertz, and a power output of 0.4 watts. Its detection range was adjustable between 15 and 70 feet, while battery life lasted for 20 to 30 seconds after activation. The signal processing included 4 stages of amplification. Despite its intricate internal mechanisms, the fuse's operation was straightforward. Upon firing setback, the electrolyte ampule broke, activating the battery. Centrifugal force from the shell's spin armed the detonator after 0.8 seconds. The oscillator transmitted signals while the receiver listened for returns. When a reflected signal indicated that a target was within lethal range, the Thurotron switch discharged the firing capacitor. This entire sequence, from detection to detonation, occurred in just 0.0003 seconds. Admiral Richmond Turner, who commanded amphibious forces during the Okinawa invasion, credited proximity fuses with making the operation feasible. He estimated that without these fuses, losses could have exceeded 150 ships sunk, potentially causing the invasion to fail. This technology saved tens of thousands of American lives. The effectiveness of proximity fuses influenced Japanese strategic decisions. In Emperor Hirohito's surrender announcement, a new and particularly devastating bomb was mentioned, presumably referring to atomic weapons. However, Japanese military records also indicated significant concern over conventional defense improvements. In July 1945, an Imperial Navy study found that enemy anti-aircraft capabilities had advanced to the point where special attack operations no longer yielded favorable exchange rates. Interviews conducted as part of post-war strategic bombing surveys revealed the significant impact of proximity fuses. Admiral Somu Toyoda, who served as Chief of Naval General Staff, stated that they estimated 500 Kamikaze aircraft could sink 100 American ships at Okinawa. However, due to improved anti-aircraft weaponry, fewer than 30 enemy vessels were seriously damaged by the same number of aircraft. This failure made further operations mathematically impractical. The proximity fuse program demonstrated remarkable economic efficiency with a cost-to-benefit ratio that was highly favorable. The program's investment of $1.2 billion resulted in an estimated saving of over 200 major ships, valued at around $8 billion, and lives worth approximately between $40,000 to $60,000 each. It also saved $2 billion in medical and disability costs. Operational efficiency was enhanced with a reduction in ammunition expenditure by 70%. Magazine space requirements decreased by 60%. Gun crew fatigue reduced by 50%. And engagement time per target shortened by 65%. The cost-effectiveness ratio of one proximity fuse at $18 compared to a 5-inch shell at $12, combined with an average Kamikaze aircraft costing $15,000, resulted in a favorable exchange rate of approximately $500 to $1. By July 1945, the effectiveness of proximity fuses had become so pronounced that Japanese tactics underwent significant changes. Operation Ketsugo, which aimed at defending the home islands, abandoned daylight kamikaze attacks from higher altitudes and instead focused on night operations, ultra-low approaches, and exploiting poor weather conditions. Vice Admiral Matomu Ugaki, who commanded Special Attack Forces, noted in his diary on July 24, 1945, "The Americans have developed a defense that we cannot penetrate. Our young men are dying in vain, exploding harmlessly far from their targets. We must seek new methods or abandon special attacks." To counter this threat, the Japanese devised Operation Tsurugi, which involved suicide attacks using stripped-down fighters flying at wave-top height to avoid radar detection. These aircraft would approach enemy vessels at less than 50 feet and climb just seconds before impact. Although initial trials suggested potential success, Japan's surrender prevented full implementation of the plan. Meanwhile, Japanese scientists worked intensively on electronic countermeasures. Project Yashima aimed at developing jamming transmitters for proximity fuse frequencies. But despite promising laboratory results, Japan lacked the industrial capacity to produce these devices in sufficient quantities. Their most advanced prototype weighed 200 pounds and needed its own plane for transport, which negated the intended purpose. The successful deployment of proximity fuses prompted a swift transfer of technology among Allied forces. British troops utilized ground-based anti-aircraft guns, equipped with these fuses, to destroy 79% of Von flying bombs aimed at London from December 1944 onwards. Soviet forces supplied 25,000 proximity fuses through Lend-Lease and reported similar effectiveness in protecting cities on the Eastern Front. This technology spurred immediate advancements. By war's end, American researchers had adapted proximity fuses for various weapon systems, including aerial rockets, naval rockets, artillery shells, mortar rounds, and aerial bombs. Each application demanded specific modifications. Rocket fuses were designed to handle higher velocities, while artillery fuses included ground return filters, and bomb fuses incorporated barometric switches to prevent premature detonation at high altitudes. Unbeknownst to the Americans, Germany had independently developed proximity fuses using capacitive sensing technology that detected changes in an electrical field caused by nearby aircraft. Although the German design was more elegant with only 23 components compared to the American version's 134, it proved impractical for mass production due to German industrial limitations. By the war's conclusion, Germany had produced just 8,000 units, whereas America manufactured over 22 million. Dr. Hubert Schaden, the lead scientist behind the German proximity fuse project, wrote post-war that his team solved the theoretical challenges in 1940 before American efforts began. However, theory alone was insufficient without the capacity for mass production. The Americans could produce one day's worth of fuses that Germany required a month to manufacture. Statistical analysis indicates that proximity fuses played a crucial role in preventing catastrophic losses during the planned invasion of Japan, known as Operation Downfall. Scheduled for November 1945, this operation anticipated an attack by 5,000 to 10,000 kamikaze aircraft against the invasion fleet. Without proximity fuses, estimates suggested that between 400 and 500 ships could be sunk or severely damaged, resulting in up to 100,000 naval casualties. Planners revised their estimates to between 100 and 150 ships being lost, along with an estimated 25,000 casualties, numbers that were still devastating, but deemed more manageable. The atomic bombs rendered these projections unnecessary. Yet the lessons from Okinawa indicated that even reduced casualty figures might be overly optimistic. Individual ship encounters demonstrated the life-saving capabilities of proximity fuses. On May 3, 1945, the USS Aaron Ward faced multiple kamikaze attacks and managed to shoot down 6 aircraft using proximity-fused ammunition despite taking damage from 3 hits. Statistical analysis indicated that without these advanced fuses, most attacking planes would have successfully hit their targets, likely sinking the ship with significant casualties. Gunner's mate Aristides Footrides, who commanded Mount 52 on USS Laffey Ordeal, later calculated in a computer analysis conducted in the 1970s that conventional ammunition would have allowed for 14 kamikaze hits instead of 6. No vessel could withstand such an onslaught. Every sailor aboard owed their survival to proximity fuses. Lawrence Delosky added that fire control systems provided confidence after VT fuses were implemented. Prior to this, when radar detected 50 incoming aircraft, it was known that many would penetrate defenses. With proximity fuses, there was a newfound faith in the technology's effectiveness. The development of proximity fuses accelerated advancements across multiple technological fields by decades. Requirements for miniaturization paved the way for techniques later utilized in transistor creation. Mass production methods foreshadowed modern electronics manufacturing practices. Quality control standards set benchmarks still relevant today in aerospace engineering. In a 1980 reflection, Dr. James Van Allen noted that the proximity fuse program was akin to the Manhattan Project of electronics. The technology compressed 2 decades of progress into just 24 months. Every cell phone, computer, and piece of modern electronic equipment owes its existence to manufacturing techniques pioneered during this era. The initiative yielded 87 patents, introduced 12 new manufacturing processes, and trained thousands in precision electronics assembly. After the war, these workers became instrumental in establishing America's electronics industry. Companies such as Texas Instruments, Fairchild Semiconductor, and Intel can trace their roots back to proximity fuse manufacturers. Japan's post-war assessment was included in a 1952 series published by the Japanese Defense Agency. The analysis concluded that proximity fuses had fundamentally changed the strategic effectiveness of special attack operations, rendering them ineffective by March 1945. Captain Ricky Hay Inaguchi, who served as a senior staff officer for Kamikaze operations, wrote about this in 1958. He noted that the development of proximity fuses was not just an incremental technical improvement, but rather represented a paradigm shift. It transformed anti-aircraft fire from being probabilistic to deterministic. Our pilots were no longer facing random danger but systematic destruction. Admiral Takejiro Onishi, who initiated the Kamikaze program, committed suicide on August 16, 1945. In his note, he expressed regret for sending his subordinates and their families to a futile death. Historians attribute this despair in part to the effectiveness of proximity fuses. Throughout 1945, continuous improvements were made to these devices based on combat experiences. The Mark-58 model introduced in May 1945 incorporated lessons learned from Okinawa. It featured enhanced discrimination circuits that reduced false triggers by 90%, variable sensitivity settings for different target sizes, improved countermeasures to defeat Japanese jamming efforts, and a battery life extended to 35 seconds. The components were also miniaturized, reducing weight to just 9.8 ounces. The Mark-59 model, which was ready when Japan surrendered, would have included micro-alloy vacuum tubes that increased reliability to 99.2% while lowering costs to $11 per unit. The proximity fuse program highlighted the adaptability of American industry. Factories that had never produced electronics before could transform overnight into precision manufacturers. For instance, Zenith Radio Corporation's Chicago plant switched from making home radios to producing proximity fuses in just 6 weeks. This initiative required unprecedented collaboration among competitors like RCA, Westinghouse, General Electric, and Sylvania, who freely shared patents and manufacturing techniques. Trade secrets typically closely guarded during peacetime were published weekly in bulletins distributed to all manufacturers involved in the program. During the Pacific War, proximity fuses had a significant impact, with 22,773,481 units produced and approximately 5.3 million deployed in combat. These fuses were 7 times more effective than traditional ones, leading to a 70% reduction in ammunition usage and saving an estimated 40,000 to 60,000 American lives, along with over 200 major warships and roughly 500 smaller vessels. Japanese losses attributed to proximity fuses included more than 28 Zero aircraft destroyed and about 42 Zero pilots killed. The effectiveness of kamikaze attacks dropped from 28.7% to less than 10%. The economic benefits were substantial, with a $1.2 billion investment resulting in approximately $10 billion saved through reduced losses, yielding an 8.3-1 return on investment. Admiral Mark Mitchell, the commander of Task Force 58, submitted his final action report on August 20, 1945. The proximity fuse was deemed a critical technology that defeated Japanese special attack tactics. Without it, our losses would have been unsustainable. With it, kamikaze attacks became an exercise in attrition. In the war's last month, Japanese kamikaze units achieved only a 2.8% success rate, with 97 out of every 100 pilots failing to reach their targets. Captain Joseph N. Wright, commanding USS Archfish, succinctly summarized the impact. Proximity fuses didn't just shoot down planes, they shot down an entire military philosophy. The Japanese believed spiritual superiority could overcome material disadvantage, but proximity fuses demonstrated that technology properly applied defeats fanaticism. These fuses set principles still guiding modern military technology, such as miniaturization multiplying power. Fitting radar into shells proved that size reduction increases military effectiveness. Every contemporary smart weapon traces its lineage to proximity fuses. Production capacity was key. Germany's superior design meant little without the ability to manufacture millions of complex devices, which America demonstrated as decisive in winning the war. Integration over innovation. The proximity fuses did not incorporate any groundbreaking components. Instead, they cleverly combined existing technologies. Modern military strategy stresses system integration rather than revolutionary breakthroughs. Automation saves lives by eliminating human decision-making in high-stress combat situations, which greatly enhances effectiveness. Today's automated defense systems are based on the principles of proximity fuses. Radar proximity fuses were a pivotal yet often overlooked technology from World War II. Although the atomic bomb brought the war to an abrupt end, proximity fuses had already made invading Japan feasible by neutralizing the kamikaze threat. Without these devices, American casualties might have escalated to levels that would have rendered continued warfare politically untenable. The statistics only partially reveal the story behind them. Every number represents young Americans who survived because shells detonated at just the right moment, and young Japanese whose sacrifices went unfulfilled as their planes were destroyed midair. Proximity fuses transformed the final act of the Pacific War from mutual carnage into overwhelming technological dominance that rendered further resistance futile. These fuses were more than weapons. They embodied American industrial and scientific superiority. They declared that no amount of bravery, willingness to die, or spiritual devotion could match the material advantages of a fully mobilized democracy. The kamikaze pilots offered their lives, but proximity fuses made such sacrifices irrelevant. Sailors who witnessed kamikazes exploding midair, workers assembling components without knowing their purpose, and scientists solving seemingly impossible problems were all part of democracy's response to totalitarian fanaticism. This answer came in the form of 22 million proximity fuses, simply stating that American technology would safeguard American lives regardless of the enemy's willingness to pay any price. The proximity fuses did more than just destroy aircraft. They shattered the core belief of kamikaze warfare, that spiritual resolve could overcome technological inferiority. Against American radar systems, which were miniaturized and mass-produced, the divine wind became a mere footnote in history. The Japanese military ambitions, fueled by the rising sun, met their end at the hands of radio waves and vacuum tubes smaller than a sake cup. This was the ultimate irony. Japan had attacked Pearl Harbor to prevent American involvement in its expansion, yet they concluded the war watching their most dedicated pilots perish futilely in empty skies, victims of American technology that seemed almost supernatural. The proximity fuses turned their greatest sacrifice into sheer waste. These radar proximity fuses were democracy's ideal weapon against fanaticism, not by matching sacrifice with sacrifice, but by rendering it irrelevant through superior technological advancements. They triumphed through production and innovation, safeguarding life rather than glorifying death. This victory marked not only the end of the Pacific War, but also laid the foundation for American military dominance that continues to this day. The Kamikaze were meant to die, but the proximity fuses ensured their deaths achieved nothing. In this reality, Imperial Japan's defeat and America's democratic triumph were measured in electronics rather than courage, in science instead of spirit, and in technology that prevented death rather than glorifying it.